Hello. In this section, we are going to introduce the topic of sequences. So, first, a little bit of why we care about sequences in a very vague sense that we will get to in the next sections and next few weeks is that we have kind of reached a point with integrals where some integrals are really hard to work with, and some functions in general are really hard to work with, whether it be limits or integrals that we want to do, or even often derivatives. And so we're introducing another area where we can take some of these functions that are really hard to work with and approximate them with things known as power series. So functions can be approximated with power series. And what is a power series? We are going to build up to that. But first, we're going to have to talk about what are just series in general. And to be able to talk about what a series is in general, we want to talk about what a sequence is. So, because we want to get to this world of being able to work with things that can help us approximate functions, we need to build up to that with what is a sequence and then what is a series before we then get to what is this power series we can use. So, what is a sequence? A sequence is an infinite ordered list of terms. For what we will be working with, these terms are numbers. It is an infinite list. So, as an example, we could have the list that goes 2, 4, 6, 8, 10, and so on. And we know that sequence, what pattern is happening is adding 2. We could continue on that pattern. And we know in this list, the first term is 2, and then the second term is 4. So there's an ordering to it. And this list can go on and on forever. A series is the sum of an infinite ordered list. So it is the sum of a sequence. So we're going to take a sequence and then add all the terms together. So like 2 plus 4 plus 6 plus 8 plus 10 plus so on. And we will continue with this idea of convergence and divergence, where converging for a series is going to mean I can add up all these numbers and get to a singular value. And divergence meaning I can't add them all up and get to a singular value. But we will continue talking about that idea of convergence and divergence for series in the next sections. But today, and in these videos, we're focusing on specifically sequences. So again, back to what is that sequence? As already defined, it is an ordered list of numbers. And we can define a sequence in 2 ways. The first is known as a recursive formula. And what a recursive formula does is it takes the previous term in the sequence, an minus 1, and it applies some rule. And we often write rules as functions. So it says, I have my previous term in the sequence. I apply some rule to it. and that gives me my next term in the sequence. Using this 2, 4, 6, 8, 10 example, the rule is that for the next term in my sequence, I take my previous term and multiply, or add, I should say, we added 2. And with recursive formulas, we also need to state where did it start. So in this sequence, our first term, a sub 1, is 2. The first term in the sequence is 2. Then, if I want to find a sub 2, I take the previous term, a sub 2 minus 1, and add 2. Which is 2 plus 2, which is 4. So the second term in the sequence is 4. The third term takes the 4 and adds 2. That is the recursive formula. I should say, for a recursive formula, a sub 1 equals some number. In our specific example, a sub 1 equaled 2. An explicit formula is very much like we think of regular functions, where typically with a function, say y equals f of x, we'd say, oh, my input at x equals 3, we'd plug 3 in and get our output. That is what a recursive formula does, but n is now our input, and our output is a sub n. So this is just like a function, but our inputs are only whole numbers and mostly non-negative whole numbers. So when we're working with the explicit formula, it is like a function. So in this case, our explicit formula for 2, 4, 6, 8, 10, 12, 14, what we're doing is we're taking whatever input we're at and we're multiplying by 2. Right? The third term of our sequence is 2 times 3. The fifth term of our sequence is 2 times 5. So if I were to write a formula for this, it would be that a sub n equals 2 times n. So once again, a sub 1 would equal 2. A sub 2 would equal 2 times 2. And so on. So sometimes the easiest thing to work with is going to be the explicit formula. Sometimes the easiest thing to work with will be the recursive formula. But let's take a look at some different ways of how these formulas can then be presented. So in our first example here, 2, 6, 10, 14, 18, this is a list of numbers. And we see to go from one number to the next, we are adding 4. Plus 4. Plus 4. So if I wanted to write the recursive formula for this, it would be, I'm taking the previous term and adding 4, where my first term of the sequence is 2. If I wanted to write an explicit formula, the thing that I notice is that there is a common difference over and over. What this pattern should generally feel like is a pattern of a line, where when my input is 1, my output is 2. When my input is 2, my output is 6. My input is 3, my output is 10. Input of 4, output of 14. And we could use this to create an equation of a line. That equation of the line is going to be the same equation that we would use for the explicit formula. So if this was my input-output table and I needed to find the slope of the line, for every one increase in my input, I have an increase of 4 in the outputs. So the slope is 4. So 4 times n to be that linear part. And now I just need to adjust so that when I plug in 1, I get 2. Well, if I plug in 1 currently, I get my first term to be 4. I need to subtract 2. So when a sub 1 is what we want to find, we would plug 1 into this and we'd get 2. If I wanted to find a sub 2, I'd plug 2 in, which is 6. So we could check the rest of those, but the explicit formula is just the same way we would find an equation of the line normally. So we could write sequences as just that list of numbers without using the formulas, but then the formulas will help us work with them later. In this next example, the one in the upper right corner now, this is already the recursive formula. See, we have a formula that is based on what was the previous term. So we're told the first term is 3. So then the second term is going to be, what if I plug in 3? So 4 times 3 minus 5. 12 minus 5 is 7. So the second term is 7. The third term would be taking a sub 2, 7, and plugging that in. 4 times 7 is 28 minus 5, 23. The fourth term would be taking 23 and plugging it in and subtracting 5. 23 times 4 is 92. 92 minus 5 is 87. And we can continue that pattern taking the term before. So there is an example of it being written in the explicit, in the recursive form. And then we'll look at now this bottom left example. This bottom left of the a sub n equals -1 to the n is in a explicit form where we're saying n is going to be these whole numbers, 1, 2, 3. There's my inputs. We often end up dropping those unless we need to say we're starting at a certain value, but these are just saying my n's are going to be these positive numbers. So a sub 1 would be -1 to the first. -1 to the first is -1. A sub 2 would be -1 squared. -1 times -1 is 1. A sub 3, -1 cubed is -1. So if I were to write it as a list of numbers, we can see this pattern of switching back and forth between 1 and -1. If I wanted to write this as an recursive formula, when I switch from one to the next, I am multiplying my previous term by -1. So the recursive formula for this would be a sub n equals my previous term times -1, or it's the negative of a sub n minus 1, where my first term is -1. Looking at the next example in the bottom right corner, we have another explicit formula, 1 minus 1 over 2 to the n. And again, that's just meaning this is like my function, but all I can plug in are the numbers 1, 2, 3, 4, 5, 6, 7. So my sequence would start when I plug in 1. And 1 minus 1 over 2 to the first is 1 minus 1/2. 1 minus 1/2 is 1/2. A sub 2 would be 1 minus 1 over 4. 2 squared is 4, which comes out to be 3/4. A sub 3 is 1 minus 1 over 8, which gives us 7/8. You might start seeing the pattern. You might want to try a few more terms, but the sequence ultimately will then look like 1/2, 3/4, 7/8, 15/16, 31 over 32, and so on. And as we're doing this formula, we're going to talk about it later, but as we see more and more terms, we're going to be asking the question about these sequences is, are these terms getting closer and closer to one number? So like in this first example, 2, 6, 10, 14, 18, we know the behavior of a line. That's just going to keep increasing, and that those numbers are going to keep increasing closer and closer to an infinite amount. So thinking about, are these getting closer to one number? The first one, no, it's not getting closer to one number. It keeps growing. Second one, same thing. No, it's not getting closer to one number. It is growing quite a bit, going from 3 to 7 to 23, then all the way to 87. The repetitive -1, 1, -1, 1, -1, 1 also is not getting closer and closer to a single number. It keeps bouncing back and forth. However, on this last example, the 1/2, 3/4, 7/8, 15, 16, 31, 32, the fractions, the numerator is always 1 less than the denominator, making, as those denominators are growing, these fractions are getting bigger and bigger, but they're never going to get larger than 1. So when we start talking about the idea of limits, the limit of this sequence is that it's getting closer and closer to 1. And then the last two examples. First, looking at the 1 over 3 to the n. We can write it just in brackets, but formally, if we have this n equals 0, that is telling us where our n starts. Most often, n will start at either 0 or 1, and we will go from there. That is the information that's always being told to us in this extra part of either this n equals 0 or in these examples, we started at 1 instead. So this sequence starts at 0, and this is the recursive, that is the explicit formula. A sub n equals 1/3 to the n. So if I were to write out terms of this sequence, since I'm starting at 0, it would be, what is it when n equals 0? Well, 3 to the 0 is 1. 1/1 is 1. So the first term, a sub 0, is 1. The second term, a sub 1, is 1/3. The third term, when n equals 2, is 1/9. 1/27 is when n equals 3, n equals 4, 1/81, and so on. We can also write this recursively and say, what is happening between each of these terms is I'm multiplying by 1/3. So a sub n equals 1/3 times the term before it, a sub n minus 1. Where a sub 0, because I'm starting at 0, is 1. Again, if we thought about this in those terms of, are these numbers getting closer and closer to a number? The numerator is always 1, but this denominator is getting really, really big pretty quickly. So these fractions are getting closer and closer to 0. So if we talked about a limit of this sequence, the limit would be 0. And now for the last example of this video is, what if we're looking at this 4 plus sine pi times 2n plus 1/2. When n equals 0, we'd have 4 plus sine of 2 times 0 is 0, plus 1, 1. We have sine of pi/2. Sine of pi/2 is a positive 1, so this comes out to be 5. When n equals 1, we'd have 4 plus sine of 3 pi/2. Sine of 3 pi/2 is negative 1, so this works out to be 3. A sub 2, 4 plus sine of 5 pi/2. 5 pi/2 is back around to sine coming out to be 1. So 4 plus 1, 5. And the last one, a sub 3, 4 plus sine 7 pi/2. 7 pi/2 would be the same as 3 pi/2. And so sine of 7 pi/2 is negative 1, making that a sub 3 being 3. So my sequence as a list would look like 5, 3, 5, 3, 5, 3, and so on. And so one of a few of things to note is, first, we can write similar patterns in many different ways. For example, this could also be written as negative 1 to the n. Because that's all it was doing, was it was either adding 1 or subtracting 1. And we'll see some other ways to write negative 1 to the n in the next few sections. The other thing to note is, again, in that idea of a limit, this is also bouncing back and forth between 5 and 3, never settling in close to one number, just like the negative 1, 1 pattern. So this sequence, if we were talking about limits, would not have a limit. In the next example, we will look at some application wording of sequences as we continue through this section.